Okay, so in this lecture, we are going to talk more about the detailed steps of a Newton-Raphson approach. Compare with Gauss-Seidel method. The Newton-Raphson method is based on the linearization of the original nonlinear equation. But nonlinear equation here, it is the power flow equation. So I first find the Jacobian, which include all first-order partial derivative of the function. And at each iteration, we solve a linear equation based on Jacobian. For instance, if we know the power and real power and the relative power, we're going to solve angle and voltage. So we keep iterations until the update of the gap between the values between any two iterations are small enough within the error tolerance. So the first step is to figure out how to form that the linear approximation of the power flow equations. Because the Taylor expansion we talk about for the Newton-Raphson method is based on the in the real domain. So we first need to convert the power flow equation into two real equations. So this is our original power flow equations. So here on the left-hand side, which is the conjugate of the compressed power. Right-hand side, it involves the voltage phasors and also the admittances, which are also complex numbers. So delta here is the angle of the voltage. Theta here is the angle of the each admittance element in the matrix. So we first split it is a complex equation into two real equations. So in the real equation, we'll utilize the angle and the voltage magnitude, and also admittance also become the absolute value. So we have two equations. We call it equation 1, equation 2. So next step is to linearize this equation to get a number of linear equations. So we need to figure out how to form this Jacobian matrix. Because this linear equation is to solve the angle and the voltage based on the power, the active power and the reactive power. So for some buses, if the voltage and angle are already known, we don't need to include those buses into such a linear equation. Examples are such as the slide bus. A slide bus has the voltage, magnitude, angle both given, right? We don't have to include the slide bus into this equation. Another example will be the PV buses. PV buses have the voltage magnitude known, so we don't need to include any equation about the voltage magnitude for the PV buses. Then we can determine the dimension of this Jacobian matrix. So assume we have n buses for the entire network, n buses for n PV buses, which are generators with the P value and the voltage magnitude given. And the rest of the buses will be the PQ buses. So we have n minus 1. The 1 is a slide bus, and minus m, which is m is for PV buses. So we have n minus 1 minus m PQ buses. As I said, we don't need to include the slide bus. So here we number the slide bus as 1. So in the Jacobian matrix, we won't be able to see any voltage angle with the subscript of 1. So when we build this Jacobian matrix, we start from index of 2. And they have 4 combinations of a partial derivative, like partial P by partial angle, partial P by partial voltage, absolute voltage, partial Q by partial angle, and partial Q by partial absolute voltage. For the PV buses, their voltage magnitude don't need to be changed. They will stay at the value given. So which means if bus 2 is the PV bus. So if we calculate partial derivative with respect to the voltage magnitude at bus 2, that derivative will become infinite. So we should cross off that column if that bus is a PV bus. And for the PV bus, we only just need to solve the angle. If we solve the angle and we also use the regional magnitude together with the voltage phasor at other buses, we can calculate the Q for those PV buses, right? So we also don't need to include that raw in the Jacobian matrix. So we can maintain the Jacobian to be still a square matrix. Okay, so we just remove all the raws involved of a partial Q involving PV buses. So at the end, for all the rest of buses which are PQ buses, their partial derivative can stay in the matrix. So finally, we have the dimension of the Jacobian will be a 2n minus 2 minus m. So the minus 2 means we get rid of the 2 rows or 2 columns about the slide bus, and the minus m, which means it's just minus 2m plus m. So plus m means we add m row and m column for the PV buses. So finally, the Jacobian matrix, we can define the 4 blocks. The J1 will be the largest block, which is a square matrix. So it's n minus 1 by n minus 1. So we only just get rid of the slide bus. And the J4 is the smallest one. We get rid of the slide bus and the PV buses. And the J2 and the J3 has a symmetric structure. So they get rid of either the rows or columns corresponding to PV buses. Just use the example 6.8 on the textbook. So it has 3 buses, 1 slide bus, 1 PV bus, or 1 PQ bus. So if you calculate, the total dimension will be 3. So for that example, the Jacobian only have 3 by 3 elements. Okay, so let's go into the detailed element for the Jacobian matrix. So we keep in mind, when we form the Jacobian matrix to include all combination of a partial derivative, we need to get rid of the rows and the columns about the PV buses. So now we form this table. The J1 will be the largest one. The J4 will be the smallest one. The J1, J4 are both a square matrix. Okay, so keep in mind for J1, we include every bus except for slide bus. And for J4, we only include the PQ buses. And for J2 and J3, depend on the row and the column. So we can include either just PQ or PQ buses or PV buses as well. Okay. And J1 is about the partial P, partial delta. So we can calculate those partial derivatives just based on the equation 1, equation 2. Yeah, so it should be very simple. You just you need to calculate derivative of either a cosine function or sine function. So if original cosine function, so now it becomes sine function, right? So original sine will become cosine. So which means if you calculate Q, that will appear here. So that will become cosine function. Okay. Yeah. So I believe everybody can get those elements on your own. So let's talk about the procedure of the Newton-Raphson method for solving power flow. So we start from equation number 1 and equation number 2. There are a number of steps we need to go through. The first step is the initialization. So in the initialization, we need to know what have been given. For PQ buses, their P and Q are specified, which means they cannot change given the entire procedure. We will take whatever value given. But for those PQ buses, their voltage and angle need to be solved, which means we can start from any initial guess. So if you don't have better knowledge, you have two options. Either you just simply take a phasor 1 with magnitude 1 and angle 0, or you can make it be equal to the voltage phasor at slide bus. So in the part for the Gauss-Seidel method, we mentioned for any PQ buses, they represent the load. In order to receive active power and reactive power, they need to have the voltage magnitude slightly smaller than the slide bus and angle slightly negative. Okay, so if, for instance, you can, if it's a PQ bus, you can take like 0.95 at the initial guess of a magnitude, angle maybe -5 degrees. So you can try it. It might give you a better result, faster iteration. But if you don't believe this one, don't trust it, it's okay to simply take just 1 as initial guess. So for PV buses, which, for example, generators, their voltage are given and active powers are scheduled, which are scheduled by the, for instance, economic dispatch, which we're going to talk about in the next section. For the voltage magnitude, to form the voltage phasor, we need to give some initial guess for the angle. If you don't have better knowledge, you can take 0 or make it be the same at the slide bus angle. Because we also mentioned in order to have this generator to generate some active power, their angle need to be slightly positive. So if you want, you can make the angle be for example, positive 5 degrees as an initial guess. So in general, it can give you a faster iteration to the true solution compared to 0 degree. But if you simply take a slide bus or 0, that's also fine. Step number 2, starting from k equals 0, we need to calculate first. By using the equation 1 and 2, we can calculate the P and Q for the PQ buses, because we gave the initial guess for the voltage, and we can plug in those initial guess to the right-hand side. You can calculate the P and Q. And then we need to compare that one to the scheduled value and calculate the gap. So if this gap is bigger than the error tolerance, we need to continue the iteration. For PV buses, we only need to calculate the P. We don't need to calculate Q, because Q will be calculated at the end. So we'll have the delta P for PV buses. So next, we'll use those delta P, delta Q to form the vector on the left-hand side. Okay, and the Jacobian is actually need to be calculated based on the formulas from previous slide. And then the goal is to solve the angle and the voltage deviations by using this linear equation. So we can utilize a technique like LU decomposition to decompose the Jacobian matrix into 2 triangular matrices. And using each triangular matrix, we can apply the Gaussian elimination to solve the vector and then solve the next. So in such process, you don't need to calculate the inverse, because calculating the inverse of Jacobian can be very costly. The next step is just to update the voltage. So after solving this voltage angle and the magnitude, you can update the value from previous situation, so you can get the new value for the magnitude and angle. Okay, this finished just 1 iteration. So if we start from k equal to 0, so by now we get the value of k equals 1. Then you plug in those voltage and angle again to the equation number 1 and number 2. Then you start the iteration. So we go back to the step number 2 repeat this process until the power and the active power and reactive power they remain the same. Okay, the update is less than the error tolerance. So then we'll stop here. Any question? Actually, compared to the Gauss-Seidel method, the Newton-Raphson method is much easier for coding. If you want to use computer to run the power flow, it's very simple. You just form the Jacobian matrix, and definitely you need to update the Jacobian matrix. Then you form the column of delta P and delta Q, and you solve the linear equation. You get the update delta angle and voltage magnitude. Then you repeat. So from this slide, you can simply just make a number of functions in the computer program and just call each individual function. Like step 2, just calculate the updated value. Step 3, it just solve the linear equation, and step 4, it just update those phasors and compare. So the code can be very simple. Okay, let's use the example 6.10 to show how to solve the power flow for this simple system. It is exactly the same system we have talked about for the Gauss-Seidel method. So basically, the system is same as the system in example 6.8. But here we just use the Newton-Raphson method instead of Gauss-Seidel method. So bus 1 is a slide bus. Bus 2 is PQ bus, and the bus 3 is the PV bus. First, we need to convert the power into per unit. So this step is same as what we did earlier in the example 6.8. So for the PQ bus, so both P and Q are negative, which means they are consuming power from the network. And bus 3 only have a P is positive, which means they have a active power injected to the network from bus 3. Bus admittance matrix is very simple. For this case, each line is a short line. It doesn't have those shunt branches on both ends. So we didn't use a pi model. So which means to form this bus admittance matrix for any off-diagonal element, it's just simply the negative value of that corresponding admittance. Okay, you just multiply that admittance by -1. And so the diagonal elements, they basically just simply just the total of the two the admittances of the two branches connected to this bus. So and this bus admittance matrix is symmetric because it doesn't involve any phase shifting. So next step is we need to convert this matrix into the polar form with every element showing the absolute value and angle. Okay, and the next step, we need to form the Jacobian matrix. We have one slide bus, one PQ bus, and one PV bus, which means for the bus 3, because it's a PV bus, in the Jacobian matrix, we shouldn't see any element involving partial Q3 or partial V3. We need to get, you can form the matrix with all combination, but if once you see any element involving partial Q3 and the partial V3, you need to cross off that row, that column. So there are only just 3 independent equations. Which are those 3? The first two is actually for the PV bus and PQ bus. This is basically equation number 1, and the second is just equation number 2. Next step, there will be some labors. You need to calculate the partial derivative of all possible combinations to fit in this 3x3 Jacobian matrix. Okay, so I form 4 blocks, right? J1, J2, J3, J4. There are 9 elements. So for instance, for this element is partial P2, partial delta 2. You just use the first equation to calculate partial derivative with respect to a delta 2, right? You will get this expression. You need to do some labor. So these slides can be very useful because in the homework or the final exam, if I have to give a problem on solving Prof law using either using the Newton-Raphson method, it won't be bigger than three bar system. So it'll be very likely to be to use Jacobian matrix similar to this. So the Jacobian matrix has each element just expression about the voltage, magnitude, angle, which means they need to be updated at each iteration. Okay, so next slide is about the procedure. So we start from a initial value. Initial value with angles at bus 2 and 3 for the PV and the PQ buses, and the voltage magnitude at bus 2 for the PV bus. So let K be 0. And first we plug in those values into the equations 1 and 2. Then we calculate the P and Q at K's iteration. So right now it's just for the step 0. Then we compare with the already known value for P and Q. So we have the gap. So if this one becomes 0, we just stop, right? You're lucky, you just by one iteration, you get correct value. So in general, this one is bigger than the error tolerance. So we need to continue. So we put this gap on the left-hand side of the linear equation. And here we need to calculate the Jacobian matrix using the formulas from previous slides by taking the initial value into the formula. Then we need to solve this equation for this vector. And we use this vector to update the current gas, and we get the value for the next iteration, K plus 1. So right now, K plus 1 equals 1. Okay. Then we go back to this the second step, plug in that equation again. We repeat this process until the update on both P and Q are less than the error tolerance. Then we stop here. We just take that value at most recent iteration as the final solution of the problem. Okay, so this process only gave you a P and Q for only gave you the P value for the PV bus and the PQ bus and Q value for the PQ bus. So we still need to calculate Q for PV bus and also the P and Q for slide bus. So we just use the equation 1, 2 again to calculate the other P and Q values. So this will finish the entire process. Any question? All right, so these slides can be your guidance to solve the Prof problem for a 3-bar system in your homework. Let's go into the detailed calculations for this example. So we start from those given values and then we make some initial guess. So here we simply just make the PQ bus have voltage 1 and angle 0. That's same as the slide bus. First step is to calculate the P and Q using equations 1 and 2, and then find the update value. The next step is to calculate the Jacobian, then solve the delta V and the delta. So you see the Jacobian here has some actual numbers calculated using the initial guess. And here we just need to solve this linear equation about this vector. Because this system is very simple, you can just solve the inverse. It doesn't take you much time. So you'll get the solution, and that can help you to update update the voltage and angle to get the new value. And the new value will be plugged into the equations 1 and 2 again. And then you will go to the next step. Okay. So repeat the process. So after 3 iterations, so the updates on P and Q have been less than the tolerance, so you can stop there. So this will be the final solution for bus 2 and bus 3 for the voltages. If you compare this process to that for the Gauss-Seidel method, the Gauss-Seidel method need to take 7 iterations because Gauss-Seidel method doesn't utilize any differentials from original equation. So the rest of the P and Q values can be calculated by those 2 equations. Okay, so they solve the problem. Okay, so that actually wrap up the approach of the Newton-Raphson method. So next we want to talk about another method which is useful to calculate power flow, which is like a revised version for Newton-Raphson method, but which can be much faster. The method is called the fast decoupled power flow solution method. So it is based on some observations. So in general, most of transmission line have a very high readiness to resistance ratio. So if it's a lossless line, which means the resistance of line can be ignored, the R will be close to 0. So this ratio will be infinite. But even it's not a lossless line, it can be a very high voltage transmission line. So the conductor can be very large. So resistance can be very small. So that will make the absolute value for the admittance be about the same as its imaginary part, which is the admittance, not admittance, susceptance, because usually the each admittance, the real part will be the J, which is called conductance, and the imaginary part is susceptance. So when the R is close to 0, so this G can be ignored. So absolute Y will be basically just B. And angle will be about 90 degrees. If this is true, we can simplify the Jacobian matrix, because some elements of Jacobian matrix can be close to 0, and we don't have to include those elements in the Jacobian. For instance, in power system, usually the IT power pretty much depend on the angle difference. So if you want to deliver IT power from one bus to another bus, we need to create the difference in angle. Which means in Jacobian, we calculate the partial P by partial V. So this one can be very small. The change of the voltage is not very sensitive to cause IT power change. And also the delta Q, which is about the reactive power, it's mainly depend on the voltage gradient. It's not very sensitive to an angle difference. So which means in the Jacobian, any elements in this form, like partial Q by partial delta, will be very small. Okay. So if we color the 4 blocks in the Jacobian matrix, the J2 and the J3, which involve such type of element, will be very small. They can be ignored. So we can just simply let J2 and J3 be 0. And this gives us a block diagonal matrix for Jacobian. That makes solving the equation much simpler than the original full matrix for Jacobian. So we can, for those set of linear equation, we can decompose those equations into two groups. The first group only solve active power for the angle, and the second is only solve the relative power for voltage. So you only just need to know the J1 and J4. This one makes sense for everyone? Or anything doesn't make sense? Okay. So next, if you are solving power flow for a system which is pretty much near the normal condition, usually we expect the voltage magnitude to stay within around 5% of the nominal value, which means the per unit value will be 0.95 to maybe 1.05. So it's very close to 1. So even voltage square is roughly the voltage itself in per unit. So you remember in the original Jacobian, there are very complex formulas. We need to calculate voltage square, and this voltage times that multiplied by that voltage. So all such thing, if you are solving the power flow near the operating condition, all such thing will be simply replaced by 1. Another observation is if the voltage is 1 and the relative power, which is injection at each bus, it's much less than the local susceptance. In that example, either the example 6.7 or 6.8, you actually can verify that Q is only 0.02 times B. Okay, which means in any equation, if you see the Q and the B, definitely the B will be multiplied by voltage, because voltage here is 1. So whenever you see equation have 2 items, one is about Q, the other is about this corresponding B, you can ignore Q. So those assumptions largely simplify the Jacobian matrix. For instance, in the J1 block, or any block involving the partial P and the partial angle. So this is the accurate formula. This is the partial derivative of original equation 1. Because each voltage, this one become around 1. And this Yij become just simply Bij. Okay. And assume those angle, this angle is about 90 degrees. And those angle is very small. Very small. So that will make a total be roughly 1. So finally, what we have is simply just negative Vi times Bij. So it becomes very simple for that element. It may not be accurate, but it will give you much simpler way to calculate. Similarly, any element in the Jacobian involving the form of a partial Q by partial V, we can also simplify that one into just this form. So this item, because the theta ij is close to 90 degrees and those two is small. So the sine angle, which is near 90 degrees, will be about 1. Right, that's same. So it will largely simplify the Jacobian matrix. So we don't need to worry about the J2 and the J3 on the off-diagonal elements. So we only just consider 2 blocks on the diagonal of the matrix. For J1, which is about any buses, not including the slide bus, J4 will be any PQ buses. Okay, we just utilize the 2 approximate formulas. And if in the block 1, J1, if it's not on the diagonal, it will be just simply the product of this negative Vi and Bij. And for the off-diagonal element, there's also one Qi. That one cannot be get rid of. But because based on our observation of this one is much smaller, so we can get rid of this Q. So eventually, for the J1, any element can be approximated by the product of a negative V voltage and absolute voltage and some Bij. Okay. So we can rewrite this block in this form. So here, the B prime is actually the include all the elements which are susceptances corresponding to this block. And we calculate the inverse and multiply by the, there's a vector, include all the IT power deviations divided by the voltage. So this formula is basically, it's just a general way to represent those 2 types of equations, because here we want to solve angle. We want to solve this angle, right? So this one will be roughly in the form like a partial P divided by like a negative Vi Bij, right? So it may not be mathematically rigorous, but will have some form like this one. But if we include all the elements, it will form this equation. So there's one item which is delta P divided by V. So that came from the original, if we calculate element by element. So there will be the delta Pi or partial Pi divided by Vi. But when we solve the vector, so what does this one mean? So we have vector divided by another vector. So here, because we consider element by element division. So when we write in this way, it means just element by element division, which means you have a 1 column vector divided by another column vector, and you form the answer will be a column vector. Its element is just equal to the element by element division for corresponding entries of the 2 vectors. Any question here? For the J4, that only include any items in the form of partial Q by partial V for PQ buses. And as I said, we can get rid of the Q because in the per unit value, this item is much smaller. So we can get rid of that item. So finally, we get a simpler form to calculate the voltage directly. So this division is also the element by element division of the Q vector by voltage vector. All right. So the next question is, we only just need to figure out what is the B matrix for J1 and the B matrix for J4. So they're formed by the corresponding elements from susceptances of the regional Y matrix. For the J1, we pick any B values, not including slide bars. For J4, we only just consider those elements for PQ buses. So they have different dimensions. So eventually solving the regional linear equation can be simplified to calculate the voltage, magnitude, and angle vector directly by just one step. So fast decoupled method doesn't need to calculate any inverse. Or if it need to calculate inverse, I only just need to do it once. Doesn't need to calculate the inverse or solve the linear equation at each iteration. Okay, let's compare this fast decoupled method to a Newton-Raphson method. So this is the equation we're going to use at each iteration. So B prime, single prime, will include admittances, which actually susceptances from all PQ and PV buses. And B double prime is actually just a portion of the P single prime, but only for PQ buses. Just give you one example. So if you calculate the bus admittance matrix, you only take an imaginary part. You get rid of the real part because each admittance will have the real part, which is usually represented by G plus a JB. So you only just take an imaginary part. If we assume the first column and first row is about slide bars, we just cross off that column and row. And for the remaining part, that will be B single prime. For you to calculate will be used here. And then you take this block only about the PQ bus. That is part of the B single prime. That will become a B double prime. Then you calculate the inverse. If the network doesn't change, so the Y bus will be constant, and the B will be constant, and B single prime and B double prime are both constant. So their inverse can be solved offline. You don't have to calculate the inverse at each iteration. Okay, so the fast decoupled method uses constant B single prime and B double prime, which is equivalent using a just constant Jacobian. Remember on the in our previous lecture, we mentioned there's a number of ideas to speed up the Newton-Raphson method. The one idea is very effective idea is don't update the Jacobian very often. Okay, at least not every step. If you're able to use a constant approximate Jacobian, even at each iteration, you didn't go into the fuzzy direction to update, but it will, if you can avoid solving, updating the Jacobian, resolve the inverse, that will save you a lot of time. Because this is just approximation of accurate Jacobian. So fast decoupled method will require more iterations than Newton-Raphson method. But each iteration is very fast. It doesn't need to solve that equation, the linear equation anymore. It is overall much faster than Newton-Raphson method. So it's very useful for fast contingency screening. For any commercial power flow solvers, you can choose between Gauss method, Newton-Raphson method, and fast decoupled method. There could be even different version of fast decoupled. The difference will be mainly in this step on what assumption you have to make. You can only just utilize some of the assumptions, but not the other, to give you better estimate for the Jacobian. But that can result in different versions of decoupled method. Okay, let's use this example 6.8 again to demonstrate how to calculate fast decoupled method for this system. It's still the same system with one slide bus, one PA bus, and one PQ bus. So this step is exactly the same as earlier. This is the Y matrix, admittance matrix. So in the Y matrix, we only take an imaginary part. So we only take an imaginary part for this Y matrix. Basically, we just take those value. And because we don't need to include the slide bar, so we just cross off the first row and the first column. So finally, we only just take those 4 numbers to form the B matrix. So B matrix will be simply like this one. It's just 2 by 2 matrix. That's B prime, B single prime. And the inverse can be calculated. So this inverse is constant. We just reuse this inverse for every iteration. We don't need to update this matrix or the Jacobian matrix. What is the B double prime? B double prime is the bus, only the pico bus, because we only have just one pico bus. Basically, just this one number. Okay, so the inverse is basically just 1 over the negative 52. So it's done. We just keep using those B single primes, B double prime of their inverse matrix value repeatedly in each iteration. Okay, let's try to iterate. We start from the same initial guess. So step 1 is initialization. Step 2 is just calculate P and Q by using equations 1 and 2. This step is same. Then we have the gap, right? By comparing the schedule value and this initial guess, we have this. By now, it's exactly the same as the Newton-Raphson method. So next step will have some difference. So instead of solving the linear equation involving Jacobian, we only just use the B single prime and B double prime. B single prime just a 2 by 2 matrix. B double prime is just one element. We don't need to solve equation because those inverse already calculated offline because B matrix here are constant. So we can directly calculate angle deviation, angle update, and voltage update. So for instance, to calculate the angle update, so this is the inverse of the B prime. This is a vector of delta P divided by voltage, element by element. So each element is just correspond to that power update, which is this one, divided by that voltage magnitude. So for bus 2, that voltage magnitude is 1. Okay. Second element, basically just this delta P divided by, because this bus is a PQ bus. So for PQ bus, the voltage magnitude is given. Okay, so this is just first iteration. For angle. For voltage, that's very simple. This delta Q is actually from, let me see. Yeah, from here. Let me use different color. Voltage is 1. That is from initial guess. This is just one iteration. Okay, then you get the updated angle and voltage. So each iteration is very simple. You just plug in the updated powers into the two formulas. to give you updated angle and voltage. But you need to do 14 iterations to get the same result as that from the Newton-Raphson method. But each iteration is very fast. Okay, so eventually you can get the same answer at the Newton-Raphson method. So in the final exam, if I ask you to solve Prof law for a 3-bar system, you can choose between the Newton-Raphson method or the fast decoupled method. Okay, for fast decoupled method, you need to calculate the B prime, B double prime once, solve the inverse and just repeat using this equation, but it may take maybe 10 to 20 iterations to get the same answer. Okay, so yeah, that's a.
Do you think this way's better than this method?
Okay, this one even if you are calculating power flow for a normal system, which means all the assumptions for this method are true, this is much faster, very fast. Yeah, because it doesn't solve linear equation, it just goes straight forward to calculate. You see all the numbers there. Yeah, but the question will be, if you are solving a power flow problem and for a system the voltage is not around 1, this can be a problem. The Newton-Raphson method is still the best. So this method, to use this version of fast decoupled method, you assume voltage everywhere is very close to 1, right? Because you can simplify the Jacobian. You don't have to, pretty much the update on the Jacobian is to deal with the voltage. Every time you get voltage magnitude slightly updated, you have to recalculate the Jacobian. But if you ignore that change on the voltage magnitude, this one will be much faster. Okay, so in the practice, so if you need to solve Prof law, for instance, for some contingency analysis, after you open the line, the voltage, some voltage can be very low. Maybe the fast decoupled method is not the best one. Even it may still give you a solution, but it may take many iterations. So usually the experienced engineer will switch between the two methods to see which one can give you a method. Maybe you can also use a hybrid approach to use some the Newton-Raphson method to start the first step to give you after a few iterations. Even if it doesn't get to the true solution, then you switch to the fast decoupled method. Okay, all right. So we finished the power flow sessions, and next week we'll start the last session of the generation dispatch.